Our second lesson here of Unit 1 is looking at parent graphs of four of our different function families and then incorporating in some translations and reflection ideas. We're going to start here with linear. So at the top here we see the descriptive form of linear, y minus k equals m times x minus h. And there are a couple of different things we are able to pull from the descriptive form. The first is a starting point, hk. Now, you want to make sure you are careful about this. If you notice hk in our descriptive form, this is negative h and negative k, not h and k. What that means for you as you're pulling out your point is you need to think of it as kind of one of two things. One, you could think of it as pulling out the opposite, negative h, making it positive h. So if this was negative 2, we'd write 2. If this was positive 2, we'd write negative 2. Same thing with the k. Or you could think of it in a slightly different way, which is actually why we are thinking of it in terms of the opposite. The reason we are considering what is opposite is we're actually asking ourselves, well, what value would make this quantity here equal 0? What would x need to be so that I had 0? And then what would y need to be so that this quantity would equal 0? The reason we want them to be zeros is because essentially that's kind of orienting us towards our origin. We're finding a shifted origin. Okay, so what would make it equal 0? The other thing we can pull out is our slope, which we should have a lot of familiarity there with slope, the rise over run idea. Okay, and so here we go. I'm going to do one. My recommendation for the second one is that you then pause the video so you can give the second one a shot, and that'll be true throughout these notes. And then restart the video after you've tried the second one on your own. That way you can check did you do it correctly, or you can hear an explanation if you did get stuck. Okay, so first one. What we want to do with each of our function families is to initially turn it into our descriptive form. So we see our m and our x minus h, but there shouldn't be anything here behind the quantity. So I'm going to go ahead and subtract this 1 over to the other side to create my y minus k piece. So if I subtracted that 1 over, we'd have y minus 1 equals negative 1/2 times the quantity of x minus 2. And once we are in descriptive form, we're able to pull out our pieces, so our starting point, hk. So h is with the x, right, and k is with the y. So you can think of it as opposite, so negative 2 would be positive 2. Or you could think of it as why we are doing the opposite, which is what would make this quantity equal 0. Well, if x was 2, 2 minus 2 would be 0, and we'd be partway towards reorienting to our origin. Over here, again, either opposite, so 1, or what makes this equal 0. And 1 minus 1 would equal 0, and so that's my starting point here, 2, 1. Okay, and then my slope is negative 1/2, which is telling me that I'm going down 1 over 2, or I should say down 1 right 2, or up 1 left 2, whichever way you prefer to think of it. So down 1 right 2, or up 1 left 2, and we've got our linear equation here. Okay, so go ahead and pause the video, give that second one a shot. Okay, turning this into our descriptive form, let's subtract this 3 over to the other side. Y minus 3 equals 2 times x plus 1. Pulling out my coordinate point, what makes this equal 0? X would need to be negative 1, or you could think of it as opposite. Positive 1 becomes negative 1. Over here, opposite of negative 3 is positive 3, or what makes this equal 0? If y was 3, we'd have 0. And so there's our shifted origin. And then my slope is 2 here, right, or 2 over 1, which means I'm going up to right 1, or down to left 1, whichever way is your preferred way of thinking of it. So up to right 1, or down to left 1. And we've got our line. So linear, I know that linear functions is something you started working with a number of years ago, but the nice thing about getting the linear function idea under your belt is that you're going to see some pretty striking similarities between what we just did and the rest of our function families. Okay? So linear absolute value is next. Again, we start with our descriptive form here, y minus k equals a times absolute value of x minus h, which looks very similar to our linear form, our linear descriptive form up here. Right? So we still have our starting point, our hk. It's still the opposite, or what makes this equal 0. So all that's the same. And we still have slope, the rise over run idea. The only thing you need to make sure you're careful of is that an absolute value makes what kind of shape on a graph? A V. And so make sure you're thinking ahead of time when you first look at an absolute value equation that, okay, I need to make sure I end up with a V on my graph. And then make sure you're thinking about, is this going to be an upward facing V or a downward facing V? So quickly think about real fast, what shows us we're an upward or a downward facing V? And that's your slope. So if you have a positive slope, you're faced upwards. A negative slope, you're faced downwards. And you'll see that in the quadratic as well. Okay, so here we go. First one's for me. Let's go ahead and turn it into our descriptive form. We don't have anything behind the absolute value, so let me add this 2 over to the other side. Y plus 2 equals 3 times the absolute value of x plus 3. Okay. And then we're going to pull out our point. Again, it's that idea of opposite, or what makes this equal 0. So my x would be negative 3, and my y would be negative 2. And that's the vertex of my absolute value, negative 3, negative 2. Okay? And then we're going to be looking at our slope. Our slope here is 3, or 3 over 1, which is up 3, right 1. Now, in this case, it's not also down 3, left 1, like the linear is, right? Because we do need to end up with that V shape, so we do have to leave it as up 3, right 1. So up 3, right 1, and we have the first part of our absolute value. The reason that, again, that we can't think down 3, left 1 is because I need a V. I'm actually going to end up kind of reflecting this over on the other side. So I'm still going to go up 3, but now rather than going right 1, I'm going to go left 1. And I've got the other side of my absolute value. And again, it's facing up, because a positive slope means I face up. I have a positive slope, so I'm facing up. Okay, the next one's yours. Go ahead and give it a shot. Okay, so we have y equals negative 1/2, absolute value of x plus 3. We go ahead and subtract this 3 over to the other side. Y minus 3 equals negative 1/2, absolute value of x. Okay, my coordinate point. What's the opposite, or what makes this equal 0? Well, on the x over here, I have no number in here. That's 0. Again, because what makes x equal 0? Well, 0 makes x equal 0. Okay, on the other side, my y will be 3, positive 3. Okay, so 0, 3. My slope is negative 1/2, which tells me that I know I'm going to be facing downwards. So it's going to be down 1, right 2. So down 1, right 2. So there's the first part of my absolute value. And then remember, it's not just up 1, left 2. Because we aren't making a linear, we're making a V. This is an absolute value function. So we're still going to go down 1, but then rather than going, oops. 1 second. I went down 2, right 1. Sorry about that. Quick little cleanup here. Sorry about that, guys. Down 1, right 2 is here. There we go. So I'm still going to go down 1, but rather than going right 2, I'm going to go left 2 to create that V. Okay, and it is, again, downwards facing because we have a negative slope. Okay, and so that's absolute value. Quadratic is up next. Quadratic, again, descriptive form, looking very similar to that linear absolute value or the linear descriptive form. We still have our y minus k, we still have our x minus h, so our starting point is still going to be hk, the idea of opposite, or what makes it equaling 0. What makes quadratic, though, slightly different than the other two is quadratic does not have a slope. I know it looks like we do. We still have our stretch here of a, but think about what a quadratic function looks like. Quadratic function is a u, right? Meaning that I don't have a consistent slope. As I work my way around the u, my slope is actually increasing or decreasing depending on which direction I head. And so I'm not going to have this whole idea of consistent, like up 1 over 2 or that kind of thing. Instead, your quadratic, and so this is, like I said, the slight difference, your quadratic, we're going to move a over 1. Our a, again, being what looks like slope. And this is only going to happen for the first point on either side of our vertex. That pattern of a over 1 does not keep happening because, again, the quadratic slope is not consistent. Technically speaking, the next step after that first one is our a over 1 times 3. And then it continues to increase like that as we go on. But we're really only concerned at this point with coming up with 3 points. So our 3 points for our quadratic are going to be our vertex, our hk, and then the 2 points that result from doing a over 1. Okay? Again, you always want to think about what your graph should kind of sort of look like. So if my a is positive, so positive a, I should have an upward facing u. A negative a, I should see a downward facing u, a downward facing parabola. Okay, so here we go. This one's for me. Let's turn this into descriptive form, subtracting the 3 over to the other side. Y minus 3 equals negative 2 times the quantity of x minus 2 squared. Okay. Our vertex, our hk point, so our x would be positive 2. Our y would be positive 3. Okay. And then we are moving, again, it's not slope. So we are not just looking here and automatically going down 2 over 1. It's a over 1. Okay? Now, I know you might be sitting there going, well, okay, if my a is negative 2 and I do negative 2 over 1, is that not going down 2 over 1? I mean, yes it is, but that's not going to be true, or that similarity is not going to be true when you get to fractional a's. And so you're going to see that on the next one. So yes, I know it kind of seems like we are doing slope of like down 2 over 1, but again, it's a very minute difference. Our a over 1 is negative 2 over 1, and so we'd be going down 2 over 1. And again, this is only for the first point on either side of our vertex. We do not keep doing that down 2 over 1. Quadratics are not consistent, right? Okay, and so then you've got your graph. Okay, so we've got our u here. We're done. Okay, go ahead and pause the video, give that next one a shot. Okay. Turning into descriptive form, let's add that 2 over to the other side. Pulling out our hk, our vertex, we have negative 1 and negative 2. And then here's where you're going to see that difference in the a over 1 idea besides slope, or in comparison to slope. If 1/2 was slope, we'd be going up 1 over 2. That's not what we are doing here. Okay? Our slope, or our movement is going to be a, or 1/2, over 1, which means up 1/2 over 1, which puts me here. The reason it's important that we realize that it's not the same as up 1 over 2 is because imagine for a second, so don't put this on your paper, but imagine for a second if I had done up 1 over 2, where would that point have landed me from this vertex? It would have landed me here. Well, technically speaking, the next point on your quadratic, besides the 3 we have written, is actually here. My quadratic never passes through that coordinate point. But if I had done slope, up 1 over 2, that coordinate point is where I would have landed. And that's not part of my quadratic. So again, quadratic does not have slope. It's a over 1, up 1/2 over 2. Okay, so we've got our 3 points, 1, 2, 3, up 1/2 over 1. And so we can go ahead and sketch this in. And we've got our quadratic. Okay? Okay, exponential. Now, exponential is usually a little bit trickier for some people. So if you notice, we have 3 examples here. So I'm going to leave this up to you as you're watching. If you feel like after one example you're like, I got this, I want to try it on my own, well then go ahead and pause it. And try the second example on your own, or restart it either when you have an answer or when you get stuck. But if you watch the first one and you're like, I don't know about that one, then maybe watch the video through for a second example before you pause it and try the third on your own. That's where you need to make sure you are owning your education, being honest with yourself, right? So, exponential descriptive form still has a lot of similarities to the others, right? We still have our y minus k, our x minus h. We still have a starting point, hk. It's still the opposite, or what makes that equal 0. Okay. One of the differences, though, with exponential is that this starting point actually is not a point on my exponential. This starting point is actually my asymptote. Okay? So while you're still going to pull it out, it's going to be your asymptote. So let's go ahead and turn this one into our descriptive form. We have y, adding this 2 over, plus 2 equals 2 times 1/4 to the x minus 1. Okay, my hk, my x is going to be positive 1. My y is going to be negative 2. But again, this 1, negative 2 is not a coordinate point on my exponential function. It's my asymptote. So if I went to 1, negative 2, I'm actually going to put a little hole there, because it's not actually a coordinate point, and I'm going to draw my asymptote in. Okay? And then we need 2 more points. Okay, so then at this point it comes to plugging in values, kind of an XYT chart of sorts, and figuring out where those coordinate points would lie. Now, there are some advantageous x values to plug in, although ultimately speaking, you really can plug in any 2 values as long as you can see that curve. If you feel like you need to plug in more than 2 values, go ahead and do that so that you can see the exponential curve come into being. But if you want my recommendation, the first point you should plug in is the x value that you've already found. Okay? So if I took this x value and I plugged it in to my function, so y equals 2 times 1/4 to the, taking this x value and plugging it in, 1 minus 1 minus 2. The reason that I make the recommendation to plug in this x value first is because look at what that does to your exponent. 1 minus 1 is 0. And 0 as an exponent is a really nice one to evaluate. 0 as an exponent makes whatever the base is 1. Well, except for, I guess I should go on record for saying 0 to the 0 is a indeterminate form. Okay, but it makes 1/4 to the 0 equal 1. So this entire term here is going to equal 1. So we have 2 times 1, or 2, minus 2, which is 0. And so I have a coordinate at 1 for my x, 0 for my y. 1, 0. And then you have to decide what other point you want to plug in. Again, my recommendation is to not go too far from the x value that you already used. The reason why exponentials do what their name says, which is they increase or decrease exponentially, meaning the further you get from this x equals 1, either the much bigger or much smaller your y value is going to get than the one you've already found. And so I tend to recommend, since you plugged in 1, maybe plug in either 0 or 2. And there's an advantage to both, or a potential advantage to both. Go ahead and take a look at your initial equation and think for a second, what would happen if I plugged in 2? What would be maybe nice about plugging in 2? Well, if I plugged in 2, we have 2 minus 1 in my exponent, which is 1. And what is anything to the first power? It's itself. And so the exponent essentially just kind of goes away by plugging in 2. Maybe that's something that you like. Maybe that's something that you would prefer to use. Unfortunately, if this exponent went away with plugging in 2, we'd still have 2 times 1/4. So I'd still have a fraction involved, minus 2. But maybe you're okay with fractions. Maybe you like that idea. Okay, well now for a second, pretend that you plugged in 0. What would happen to your exponent then? And what would maybe be the advantage? If you plugged in 0, 0 minus 1 is negative 1. And initially I know a lot of people go, ooh, negative exponents, I don't want to work with that. But think about what a negative 1 exponent would do to this fraction. A negative 1 would take this 1/4 and flip it, making it 4. And now you no longer have a fraction that you have to work with. So again, neither one's necessarily better. It's deciding which one is your preferred kind of method. It's just deciding. So let's go ahead and model. If I were plugging in 0 first, so if I did 2 times 1/4 to the 0 minus 1 minus 2, well, this would be 1/4 to the negative 1, or 4. 2 times 4 is 8, minus 2 is 6. And so I'd have a point at 0, 6, which is slightly off my graph, but that's okay. 2, 3, 4, 5, be like here. And I could get my curve that way. Or maybe you prefer the plugging in 2 rather than plugging 0, so I'm going to do that over here. Okay, if we did 2 times 1/4 to the 2 minus 1 minus 2, or I should say this is y equals. Okay, well, 1/4 to the first power would just be 1/4. 2 times 1/4 would be 1/2. And 1/2 minus 2 would be negative 1.5, negative 3/2, or negative 1.5, depending on how you prefer to think of that value. And so we'd have a point at x equals 2, y equals negative 1.5, which is kind of here-ish. And so you could get your curve through those 2 points if you wanted to. Okay? Again, you don't have to do all 3 of these. At this point, we're only concerned with 3 points to guide our sketch. 1 is your asymptote, and so you need 2 others. I recommend, like I said, the x value that you already found and one of the ones nearby, either 0 or 2. Okay? Okay, example 2. If you feel like you got it after that first example and you want to give this second example a shot, go ahead and pause the video and restart it when you're ready. If you'd rather just kind of follow along with me, go ahead and do that. Okay, so descriptive form first. Okay, so I'm going to subtract this 4 over to the other side. My coordinate point, my x is going to be 0. My y is going to be positive 4. And again, that's not a point on my function. Exponentials, that's the little hiccup spot on exponentials that you need to make sure you're aware of. That this is the asymptote, not actually a coordinate point. So 0, 4 would be here. And there's my asymptote. And then you need to plug in 2 other values. It's your choice what you plug in. I tend to recommend plugging in the 0 that you've already found into your function. So we have g of 0 equals negative 3 to the 0 plus 4. Anything to the 0 is 1. Now careful that this stays negative 1 and doesn't become positive 1. The reason why, remember order of operations, parentheses happen first. I don't have parentheses. Then exponent. This 3 to the 0 becomes 1 before multiplication of timesing by a negative. If I had had parentheses around this negative 3, then the whole negative 3 would have happened first. Then the exponent would have happened on the outside of the parentheses. But because I have no parentheses around the negative 3, this is going to be negative 1 plus 4, which is 3. Okay? So there's my first coordinate point at 0, 3. Okay, second coordinate point, either 1 or negative 1 would be my recommendation. I'm going to go ahead and plug in 1, because if I plugged in negative 1, I'd have a negative exponent, and I don't really see a huge advantage for making the 3 1/3. Although if you'd like to, you're more than welcome to, but I'm going to go ahead and plug in 1 in this case because I kind of like leaving it the way it is. Okay, so we have 3 to the 1 is 3, so this is negative 3 plus 4, which is 1. So my second coordinate point is at 1, 1. And with that, you've got your exponential. Okay. Okay, this last one, I would recommend kind of making yours to see if you're kind of processing what we've talked about so far. So go ahead and pause the video, restart it when you're ready. Okay, descriptive form. Adding this 1 to the other side, we have y plus 1 equals 2 to the x plus 3. Okay, my HK, x is negative 3, y is negative 1. Again, that's my asymptote. So I'm going to put a hole. Okay. And then 2 values to plug in. Again, my recommendation is to start with the x value you already have. So y equals 2 to the negative 3 plus 3 minus 1, because that gives me 2 to the 0, which is 1 minus 1, which is 0. So my first coordinate point is at x equals negative 3, y equals 0. Okay. And then second value, I'd plug in something relatively near negative 3. So I'm going to plug in negative 2. Okay, so we have y equals 2 to the negative 2 plus 3 minus 1, which is negative 2 plus 3 is 1. So 2 to the first is 2 minus 1 is 1. And so my second coordinate point is that x equals negative 2, y equals 1. Okay? And with that, you've got your function. Okay, got a couple more things here to look at in 1.2. Next up, we've got some special cases. So go ahead and pause the video, and on your own, go ahead and read these two sentences, process what they are telling you. Okay? So horizontal lines are in the form y equals. So if I see y equals a number, okay, as a constant, it's like y equals 5, that tells me I'm a horizontal line, side to side. Vertical lines are in the form x equals, where again h is a constant, so like x equals 5. If I see x equals 5, that's a vertical line, or up, down. Okay, and so we go ahead, graph y equals 2, graph x equals -3, and then we'll check our answers in a short bit. Go ahead and pause the video if you need to. Okay, y equals 2, y equals a number, is a horizontal line, side to side. So y equals 2 is here, and so it's my horizontal line. X equals number, x equals a number, is a vertical line. So up and down, x equals -3 is here, and so there's my line. And those are your two special cases. Okay. Transformations are up next. So transformations. We have 4 transformations that you've learned in prior math classes, but we want to really quickly here just make sure we remember. Okay, the first one is negative f of x, which is a reflection across the x-axis, and its coordinate rule notation is that xy, or the coordinate xy, becomes x negative y. The reason that we are negative f of x or negative y when we are reflecting across the x-axis is because the x is not going to be changing, right? I'm reflecting over the x-axis. That's my focus, is x. That's my kind of anchor point of sorts, is the x-axis. And so x has to stay the same because x-axis is my line of reflection, is my anchor point. Okay, so y is going to be the thing that changes sign. Okay, the reverse is true for y-axis. So when we are reflecting across the y-axis, we have f of negative x, or in my coordinate rule notation, we have negative x. Again, the reason why the x is negative is because now the y has to stay the same. I'm reflecting across the y-axis. That's my line of reflection. That's what's anchoring what I am doing, and so the y has to stay the same. Okay. For translations, a reminder that translating right is an x plus idea. This is telling me to go right 3. And translating up is a y plus idea. This is telling me to go up 1. Translating left is x minus, so left 2. And translating down is a y minus, so down 3. Okay, so here you go. We're going to go ahead and practice some of these. For number 1 here, we have j of x equals 1/2 to the x minus 3 plus 1. Let's go ahead and turn into our descriptive form. So we have j of x, I'm going to subtract this 1 over to the other side, equals 1/2 to the x minus 3. So my coordinate point is x equals 3, y equals 1, positive 3 and positive 1. Remember, this is an exponential, x in the exponent of exponential, so that is my asymptote. Okay. And then 2 other points, you can plug in whatever 2 points you want. Okay, so again, you've heard my recommendation several times, but I would first plug in 3. So we have 1/2 to the 3 minus 3 plus 1, which is 1/2 to the 0, or 1 plus 1, which is 2. So my first coordinate point is at 3, 2. And then the second one, I'm going to go ahead, I'm going to plug in 2 for this one, because I have this fraction here. So if I plug in 2 minus 3, and then plus 1. The 2 minus 3 becomes negative 1, which will flip that 1/2 and make it 2. And 2 plus 1 is 3. So my second point is at x equals 2, y equals 3. Okay? So then we've got our little exponential function here. This is j of x. Okay? And so then graphing k of x next. So if we are graphing k of x is a reflection. We see negative x, so it's reflecting j of x over the y-axis because x is changing sign, meaning y is my anchor. And so if I reflected over the y-axis, my k of x would end up here. Right? 1, 2, 3, 1, 2, 3. And I would have my function. Okay. Describing the transformation from the first function to the second function. Okay, we're going to do our description in 2 ways. The first one is words. So it's what we just said, reflect across the y-axis. And then the second one is our coordinate rule notation, which is x, y goes to. And since we are reflecting across the y-axis, y is going to stay the same, which means x is going to change sign. Okay. Okay, number 2, exponential. So descriptive form, j of x minus 1 equals 3 times 2 to the x minus 3. Okay, my coordinate point, x is positive 3, y is positive 1. Again, that's my asymptote. Okay. And then plugging in 2 points, I'm going to go ahead and plug in x equals 3. So 3 times 2 to the 3 minus 3 plus 1, which is 3 times 2 to the 0. 2 to the 0 is 1, so 3 times 1 is 3, plus 1 is 4. So my first coordinate point is going to be at x equals 3, y equals 4. And then the second one I'm going to choose to plug in is going to be 4. So we have 3 times 2 to the 4 minus 3 plus 1. 4 minus 3 is 1, so we have 2 to the first, which is 2. 3 times 2 is 6, plus 1 is 7. And so my second coordinate point is going to be at x equals 4, y equals 7. You also could technically plug in 2. You'd get 3 halves plus 1, which is 5 halves or 2 1/2 if you prefer to kind of work with that fraction but there. Okay? Okay, so and then you've got your exponential function here. J of x. Okay, k of x. Adding the 2 over for descriptive form, k of x plus 2 equals 3 times 2 to the x minus 1. My coordinate point is positive 1, negative 2. For my asymptote. And actually just with that point I can already see what has happened for my function here. Or at least I'm pretty sure I know what's happened. It looks like a translation. It looks like a translation down 3 and left 2. Okay. If we were to finish off our graph, k of, I'm going to plug in 1 equals 3 times 2 to the 1 minus 1 minus 2, which is 2 to the 0 or 1 times 3 or 3 minus 2, which is 1. So my first coordinate point is going to be at 1, 1. which again confirms the down 3, left 2. And k of, let's put in 2, which is 3 times 2 to the 2 minus 1 minus 2. 2 minus 1 is 1, 2 to the 1 is 2, times 3 is 6, minus 2 is 4. So our next point is at 2, 4. Here. Again, confirming the down 3, left 2. Okay, sorry, I'm really quickly checking my work. Yeah, okay. And so that's my k of x. Okay, so if I know that I have translated down 3 and left 2, that coordinate rule would be xy becomes down 3 is a y manipulation, down would be minus, and left 2 is an x manipulation, left would again be minus. Okay? So, there are 2 more here. I am going to go ahead and walk through them on the video. This is where you need to make a decision for yourself. If you feel like you're getting it, well, then maybe you skip the video to the last bit, composite functions. Or maybe you pause the video and you try one of these on your own and then restart the video to double check, or whatever it is that you need to do to make sure you've understood what we're doing here. But I am going to go ahead and walk through them. Okay? So here we go. G of x, descriptive form, adding that g over to the other side. G plus 3 equals negative 2 times x squared. Okay, my HK, or my ordered pair, x is going to be 0, y is going to be negative 3. So 0, negative 3. I see that I have a negative a here, so I know my u is going to be downward facing. Remember, quadratics don't have slope, so this is a over 1, or down 2 over 1. So we're going to go ahead and do that. And remember that down 2 over 1 only applies for the first point, I should say, on either side of the vertex, or these 2 points. That negative 2 over 1 does not keep happening. My next point is not right here, because this is a quadratic, and so the slope changes as we work our way around our u. Okay, this is g of x. Okay, h of x. Take a look at what happens to h of x. h of x is negative g of x. Well, this is telling me to do a reflection across the x-axis, because x has stayed the same, but y has changed. And so if I reflect over the x-axis, my h of x ends up right here. Which is reflect across the x-axis. Or xy becomes, since we're across the x-axis, x stays the same, y will change sign. Okay. Okay, last one. Absolute value, b of x. Turning b of x into its descriptive form, we're going to subtract this negative 4 over to the other side. 3 absolute value of x plus 1. My coordinate point then, x is negative 1, y is positive 4. That's my vertex. I see that I have a positive slope. Absolute value, or linear absolute value, does have a slope. So I know I'm going to be facing upward since it's positive, and I'm going to be moving up 3 over 1. Up 3 over 1, both directions to create this v. And so there's b of x. Right? C of x, descriptive form, subtracting the 2 over to the other side. Minus 2 equals 3 times the absolute value of x. My vertex, x is going to be 0. Y is going to be positive 2. And then I have a slope of 3, so up 3 over 1, up 3 over 1, and here is my c of x. And so what have I done here? Well, I've translated down 2 and right 1. Which is xy goes to, down 2 is a y manipulation, so minus 2 shows me down 2. Right 1 is an x manipulation, x plus shows me right. Okay. Okay, last but not least, we have some composite functions. So, the composition of function g with function f is written as g of f. Now I want to make sure we take note of this. Do you see how that little circle is an open circle? This is not saying g times f. G times f would look like this, a closed circle. That's g times f. An open circle is g of f. And it's written kind of sort of two different ways. The first is with that little open circle idea. This is g of f. But the other way you could write it is like this, g of f, showing the f is inside g. And that's what this next sentence says. The function of f of x replaces the x values in g of x. Now we do want to be careful, and I'm going to come back and model this very shortly, but the function composition is not commutative. What that means is f of g of x does not necessarily equal g of f of x. They can't just switch because you feel like it. And in most cases, in a lot of cases, if you switch the g and the f, you actually result in an entirely different function. Okay, and so here's an example modeling this really quickly. So, if f of x is x squared and g of x is x minus 3, find f of g of x. Okay, well this f of g of x shows me that my g of x, which is my inside function, is getting plugged into my f of x, which is my outside function. And so again, my f of x is x squared, my g of x is x minus 3. The g of x is getting plugged into f. You're replacing the x with x minus 3. What that means is in f of x, everything's going to stay the same. The squared, if there was like a plus or a minus or absolute value or whatever, everything would still be there, except that any place we see an x, we are instead going to write x minus 3, because g of x is getting plugged into x. And so what that means is that this function, this x squared, rather than being x squared, the squared is going to stay, but the x is going to go away and be replaced with x minus 3. Okay, really quickly modeling why they aren't commutative before we practice this. X minus 3 squared, if you were to really roughly sketch that, it would be located kind of somewhere sort of over here. Okay? However, if we were to switch the order of this f and g, g of f of x, we would no longer get this function. Because g of f of x tells me that f, my f of x, is getting plugged into my g of x. Which means that in my g of x, everything else is going to stay there, which in this case is just the minus 3, but everywhere that I see an x, rather than writing x, I'm going to replace that. I'm going to substitute it for x squared. And these are not the same function, because where this function resulted in this graph, this function would result in a graph that, roughly speaking, looks like this. Right? They are two different functions. So they are f of g of x and g of f of x is not a commutative idea. You can't just switch them because you feel like it. Okay? So here we go. Two examples, one for me, and then I'm going to encourage you to pause the video and try the other one on your own. Okay, we have if f of x equals x plus 4 quantity squared and g of x equals 4x minus 3, then find g of f of x. Okay? Well, this means that f of x is getting plugged into g. So my f of x here is getting plugged into my g, which means in g, everything else is going to stay there, the 4 and the minus 3. But where I see an x, and if I have more than one x, I'd replace every single one of them. But where I see an x, I'm no longer going to write x. I'm instead going to write x plus 4 quantity squared. And then I can graph that. I graph it the same way I have all of my functions we've been practicing so far, which is to write this in descriptive form. So I'm going to add this 3 to the other side. My vertex, my HK coordinate point, is going to be x is negative 4, y is negative 3. This is a positive a, so I know I'm going to be facing upwards. And we are a over 1 or 4 over 1, which tells me I'm going up 4 over 1. 1, 2, 3, 4 over 1, which gives me a very steep u there. Okay, go ahead and pause the video, give that next one a shot. Okay, for this last one, we have g of x is getting plugged into f, and so my g of x function here is getting plugged into my f. So everything else in my f is going to stay, which is at this point just the plus 2. But everywhere that I see x, I'm instead going to write negative 2 times the absolute value of x minus 5 plus 1. Which means that if I simplified or combined these like terms here, my function would be negative 2 absolute value of x minus 5 plus 3. And then I can graph that. Putting this in descriptive form, y minus 3 equals negative 2 times the absolute value of x minus 5. My vertex, or my coordinate point, is positive 5, positive 3. And then my slope, because this is an absolute value, so it does have slope, is down 2 over 1. And with that, we have finished our second lesson.